thing that makes me blush, but that might have done it.
Ah! So I found what I was looking for. Wait. We're doing fun stuff today.
I'm sorry for harassing you.
She's not actually.
Just a little bit. What? Oh, Capricorn. I thought when you said, are you also a Capricorn, that if you were asking her if she's also Catholic, I was like, what in the world does that have to do with her birthday? My grandma's Catholic, and whenever she took me mass with her, she had to bring us huge good bag. Because I would could not sit still. She'd be like, draw. I'd be like, you'll find it again.
I just want to
So
log
I
in.
want to show you the thing one thing from the other day, because I got it all straightened out. Yeah, this one. The way that we were doing it, where we got the. Oh, they let you know that.
Yeah, our stuff wasn't the best.
I can't make this work. Yeah. I just was really excited to set their record. It was like a really simple, I almost texted you and I was like, I will just use
Oh.
I've just been looking at
Hopefully it'll be fun.
Although things are fun.
That's cool. I love doing stuff like that. Well, I've never actually done that, but I love I haven't seen it on I like to have a take out here.
Oh, yeah. realize it was time to start. Oh, not quite. All right, let's go ahead and get started. Are there any questions before we begin? Yeah.
What is the purpose of the MO diagrams? What we're trying to find the bond order, but what does that
That's so. There's a couple of things. So first, we'll investigate today like where Lewis dot structures fail. But in answer to your question, it's kind of like limitless. So for example, like when I was in grad school doing research, you can just use basic MO theory to see like, will something react? Are there even orbitals available for things to react? And then you don't have to, again, spend a bunch of time doing computational chemistry. And so what you guys got a taste of when you're using WebMO, like those calculations ran, really fast. But once you start getting into like actual molecules, like even, so let's just do an aside. So I used to work with molecules, and they're called small molecules, so this is still considered like small molecule research. So some phosphines on there. And then attached to some metal here, and there might be COs, oops, wrong way, like some COs or whatever metal you're interested in. But even something that looks pretty simple like this, now we're talking days to run calculations. And so you can, again, use all these little back of the envelope calculations with your MO theory and see like, well, do I think that there's somewhere to bond? Like, is there available orbitals? So that's ultimately like where it's going. But, again, that's like higher level in research. But yeah, that is like ultimately the point of MO theory, is that you don't have to use all that computational power to solve minor things like this. But we'll do kind of a simpler version of your question of, well, why do we care? And so let's start off. So just draw out the Lewis dot structure for warm-up of nitrogen versus oxygen. So take a few minutes to do that. Or yeah, N2 versus O2. So of course the diatomic form. So somebody tell me what N2 looks like. So single, double, triple bond. So triple bond between them. And then how many lone pairs on my nitrogen? So one on each. So it looks like that. So that looks good. And then what does O2 look like? So a double bond, and then how many electrons on there? So 2 lone pairs on each oxygen. And so now we're looking at these two. And so right now it doesn't look like we have any unpaired electrons. So again, from Lewis dot theory, we would expect, and this is again from Lewis dot. So we would expect that both are diatomic, or diamagnetic, I keep saying the wrong term. Diamagnetic, AKA, right, we assume that just, again, looking at these, there's no unpaired electrons, so it looks like they're all paired up. And so that means that they should behave the same. And so now let's test this out. And so hopefully this demo goes well. I'm only slightly nervous because I've never done this before. No, he'll be okay. But yeah. So I've never done this before, and I'm trying to get a liquid nitrogen tank on campus so that I can actually practice this as opposed to practicing it live for y'all. But oh well, we're going to do it live. So the first step, so what I have in here, I already break things. So this is liquid nitrogen. I forgot how cold it is, but it's pretty cold. And so for safety, we'll just talk about safety before we get started. So liquid nitrogen, you could actually like dip your hand in and you would be okay. But what you would never want to do is have it like pool in your skin. So like, you know, if it got caught between the webbing of your finger, it could pool up and burn you. If it like fell on the floor and then you were like stepping in it, it could burn you. So it can burn you, right, with the nitrogen. They also use it to burn off warts. And then what we have here are just 2 magnets. And so if it's diamagnetic, it'll just pass straight through. So it won't be affected by the magnet. And so that's what nitrogen does. And so let's just pour a tiny bit of nitrogen so you can see that, yes, this is going to kind of go straight through. Watch your feet. And so, right, I didn't capture any in there. It just kind of went straight through. And we can do it again after. I'm just not going to waste all my liquid nitrogen yet. And so what I have set up over here is this is a fancy way of doing it. So we have an oxygen tank. And so now what I'm going to do is put on my safety goggles. Put this under here. And so the idea is we have our little coil here. We're going to pass oxygen gas through. Stick this in. And so it'll be nice and cold. And so we should pump out of here some nice oxygen. And if we do it this nicely, it should be blue in color. So oxygen, so before I start condensing it, well, let's talk safety about liquid oxygen. Because one student actually made a joke of, are we going to blow shit up? And I was like, dear goodness, please no. Okay, so some safety tip of why that scared me so much. So if you want to scare any Schlinkline chemist, if you condense liquid oxygen in your Schlinkline, and when we're not doing this demo, I can pull up a picture of the Schlinkline, but liquid oxygen plus any organic is a bomb. And so as kind of a safety thing, and I've seen it happen once in grad school where someone condensed liquid oxygen. But what you do is if you condense liquid oxygen, so you drop your trap, so your trap would be filled with nitrogen. So nitrogen is at a colder temperature than liquid oxygen, so oxygen can condense. If you have a leak in your Schlinkline, which shouldn't happen, but again, you know, people do dumb stuff. That's why you always got to check and double check your setup. So if you have a leak and you're sucking in air, you'll eventually condense blue liquid oxygen in your trap. So if you were doing shrink line chemistry, organic chemistry, inorganic chemistry, and you dropped your trap and you saw blue, you would immediately put it back, close the fume hood, and tell everyone to evacuate the lab, and you just leave for the day. And so eventually your vacuum pump would get rid of it, and so hopefully by the next day it would be gone. But you would want to leave just in case, because it could go off and it will be an explosion. So that's. So now let's see. So now I'm just going to open up my tank here. Doing it live. Decrease that. Can't tell if that's quite. Is that looking blue? Oh yeah, that's looking blue. Okay, let's shut that off for a second. All right, so you can see that it's blue. So there's our blue color. And so that's how we know this is primarily liquid oxygen. And so now we put it through here. So notice how it kind of, and if you need to get closer, you can do this again. But it kind of hangs on, so you can see it hanging on to the magnet like that. And so again, nitrogen did not do that. So do we want to see nitrogen again, maybe? So let's repeat this. Oh, this is really cold. Whoop.
How cold is that?
Huh?
How cold is that? The test tube like instantly looks cold.
Somebody look up the boiling point of liquid nitrogen. That's how cold it is. Sorry, I'm like scaring myself. So obviously, right, oxygen is condensed in here. So as I pull it out, it's going back to oxygen. And so let's just repeat so we can see that yes, and I have a ton of nitrogen in here, so that's fine. If anybody wants to break stuff and freeze it after class, you can. So again, I'll pour it, and so nitrogen not sticking to the magnet. So again, just going straight through. Watch your toes if you're in the front. So again, didn't happen. Let's do it one more time. So again, you need to come up to the front so you can see. Oh, and I should have been wearing safety gloves. Whoops. That's okay. Yeah, that's why I have the test tube in this thing. I'll show them off, right? We even have brand new fancy ones that happen to be RCC blue, and I didn't use them. So safety first, guys. All right, so let's try one more time, and let me stick this tube in here. One more time for everybody. Again, if you need to get close so you can see that blue liquid oxygen, and now you can believe the textbooks when it says oxygen is blue. Like, damn, really? So one more time, hopefully I decrease the pressure. There we go. So one more time. And so there we can see the blue. So again, blue, liquid oxygen, and one more time for everybody. And so, yep, see how it's sticking to our magnet there? plane. So it sticks to that magnet.
Is that noise just the cold?
Yeah, that's just like, because it's like liquid hits the floor and then, becomes a gas. All right, so that is that. Are we satisfied playing with oxygen? All right, so now let me take this out so we can play with it later. Woo! That actually worked out a lot better than I expected. All right, so now back to class. I know, less exciting. But now we have to answer, and so this goes back to your question, well, why the heck do we need MO theory? Why do we care? And so let's try to answer this discrepancy now using MO theory. And so let's start, well, we did nitrogen previously, right? Yes, so we had done nitrogen, and so we can glance back at our little MO diagram that we made. And so we see that, yes, it's diamagnetic. We have paired electrons at each orbital. And so now for comparison, let's see what happens when we do the MO diagram of O2. So take a few minutes to get started. So remember, oxygen now has no sp mixing. So that's that line where it is now the p and the s orbitals are too far apart, so now there's no mixing. So see if you can either find the correct diagram to reference, or if you remember how to do it, go for it, and then we'll see if we can explain why oxygen behaved the way it did. And so for people asking, so liquid nitrogen has a temperature of 77 Kelvin, and then liquid oxygen is a little bit higher than that of 90 Kelvin. And of course, it's warming up, but pretty cold. So hopefully your diagrams are looking something like this. So with no sp mixing, we do our s orbitals first. I probably should have made myself more space. And then without sp mixing, then we have those pz's. So our pz, sigma bonding, so bonding, anti-bonding. Then we have our degenerate p orbitals from that pi bond, so px and py. And our anti-bonding. And our pz, anti-bonding. And so always count your middle once you're done to make sure you have the correct number. So we had 8 atomic orbitals going in, so we should have 8 molecular orbitals. So 1, 2, 3, 4, 5, 6, 7, 8. And then again, we're looking only at the valence electrons, so each oxygen contributes 6. So we start at the bottom now. So 1, 2, 3, 4, 5, 6. And now these are degenerate, right? So we have to put 1 in each one, since if they're degenerate, it's going to fill in the same energy level first before paying that price of pairing. And so now this answers the question of why oxygen is truly paramagnetic. So now it's paramagnetic, so it has these 2 unpaired electrons. And so because of that, that makes it interact then with the magnet. And so that's why oxygen sticks to the magnet, is paramagnetic, all because of MO theory. So now, again, we see the failures of Lewis dot structure. So obviously, Lewis dot structure has its importance. It does, give us geometry. But now MO theory just takes it to a deeper level so we can get a better understanding of the behavior. So questions? Is that what your diagrams look like? No? What happened?
So there are only 8 electrons that you have.
Oh, did I not? 1, 2, 3, 4, 5, 6, 7. Oh, my bad. So 9, 10, 11, 12. There we go. So I just had the wrong. I can't count. So my apologies. So I had the wrong HOMO. So the HOMO is actually the pi antibonding orbital. So does that look like what you got? Okay, good catch. And so now we can, let's see how the bond order is for oxygen while we're here. So what's our bond order? What do we get for bond order? So 2. So let's see. So 1, 2, 3, 4, 5, 6, 7, 8 in bonding. Minus 1, 2, 3, 4. Does that sound right? And so 4 divided by 2, so 2. And so, of course, that matches with at least our Lewis dot structure. So we can see, okay, we do have, a double bond. That's kind of confirmed. It's just that these electrons are occupying, again, in these antibonding orbitals. All right, let's do another one. And so again, we'll see the power of MO theory. And so this also works for different atoms. So we can look at CO now. And so CO, we can invoke sp mixing. And so go ahead and see if you can kind of sketch out a diagram. And if you want to be proper about it, oxygen should be slightly lower in its orbitals since it's more electronegative. We'll just start sketching that out. And again, invoking sp mixing now. We'll have to see. I have to draw it out. Or you tell me what you got.
I got a mess.
It shouldn't be a mess though, because it's the same diagram. So let's start drawing this together. So right, anytime we see SP mixing, you can always reference where it is. Where is it? I have too many notes. Eventually I'll find it. Well, now I don't know where it went. Dang. There it was. Okay. So right, anytime we see SP mixing, you just follow the same order. And the only difference is how many electrons you have. And so let's draw that. And so I'll just put carbon on this side, oxygen on the other. If I want to be proper about it, so I'll try to put these p orbitals just a little bit higher. And oxygen's a little bit lower. And so again, we're invoking SP mixing. Now we have our most favorable combination. Then after that, we said we had our formally anti-bonding, but not as bad combination. And then from there, our p orbitals. So our degenerate pi bonding orbitals. I won't draw py. And then above that, so again, we had that switch once you have SP mixing. And now I call this almost our non-bonding but formally bonding orbital, where we have less electron density in the center, but they're in phase. And of course, we have to have our pi anti-bonding. And then our most unfavorable interaction, where they're out of phase and the electron density is in the middle there. And so carbon's contributing 4 valence electrons, oxygen is contributing 6, so we have 10 total in the middle, and hopefully I can count this time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so now this would be considered, right, our HOMO, our highest occupied molecular orbital. And so now if we're thinking about how CO can bond, right, this is going to be what it's interacting with. Also, you can also have like pi back bonding interactions with CO, since it has this empty orbital. And so this could do some pi back bonding. And again, this would be kind of almost beyond the scope of our course, but we would find that this can do some pi back bonding with metals, and all that means is, so your d orbital, if you remember the shading on this, looks something like that, except I should have drawn it the other way so it matches up better. So let me redraw that. Right, so these are your d orbitals where they have this sort of shading, and if you look, this matches up with your pi anti-bonding orbitals. So you have your out of phase, and so your pi, you could have some pi back bonding interactions from there. And so again, this would be from a metal to CO. And then you find that CO does bond to metals, and then what's also funny about CO is that it bonds from the carbon. And so those 2 electrons are actually donating. That would be a dative bond from the carbon to the metal, and dative meaning 2 of those electrons are going to the metal there. And then what makes that even stronger is, like I said, this pi back bonding interaction where the metal can dump electrons back into this antibonding orbital and make a favorable interaction there. And so again, kind of beyond the scope of this course, but you're kind of seeing why this is useful. And if you went on to inorganic chemistry, you would do a lot more fun with this. All right, so main point was just as long as you can get your CO diagram, and then let's go ahead and calculate our bond order just so we can compare. So I should have labeled this better so we can tell who's who. So what do we get for a bond order? So 3, that's what we expect. So let's just go through it. So 1, 2, 3, 4, 5, 6, 7, 8 in bonding orbitals, minus 2 in this antibonding, or formerly antibonding. And so yes, now we get 3. And that matches right with our Lewis dot structure for CO. From this one here, this sigma antibonding. So it's just formally antibonding, since again our shading doesn't match it up, even though we kind of minimize our electron density here. Questions on this? So let's look at other stuff, even though it's kind of a review now. And so I feel like you kind of get the picture that we can knock ourselves crazy calculating bond orders for anything. So that's all the textbook goes through for the rest of the chapter, right? You can stick negative signs and plus signs on all these things. The only difference is how many electrons are in there. And so again, just understand which diagram to use. So if you're invoking SP mixing, then you're picking this order. No SP mixing, these diagrams, and then you just fill in the appropriate number of electrons and calculate bond order and everything. And then of course the higher bond order just means you have a stronger bond, and then shorter, and then we could use again like WebMO or something to calculate bond lengths and kind of compare. And so the next part of this chapter should be kind of a review from chapter 8, since we talked about hybridization in chapter 8, since again hybridization and geometry go hand in hand. So before I scroll down, so we're looking at our carbon centers. So what's going to be the hybridization on these 2 carbons? So sp3, exactly, and you examine, right, each one individually. So look at it, see that it's attached to 4 things and no lone pairs, so sp3. And of course this gives us the tetrahedral geometry, so you can see that each center is tetrahedral. And so now down here is just our sp3 mixed orbitals now. And so we kind of went over this before, but all we're doing is if we could combine, pz, px plus py, and of course s. So if we just smash them all mathematically, so of course, if we did math, it would spit out this pretty picture, but we're not going to do math. We're just admiring the pictures, and kind of, if we could smash them all together, this would give us our tetrahedral geometry. And so that's all that's shown here. So now we're seeing, again, what orbitals are interacting. So we have our sp3 hybridized orbital, and of course making sigma bonds with all our hydrogens. Of course, hydrogen, right, only has the s orbital. So all our sigma bonds. And then, of course, this leaves us with a single bond here. We can tell that just from our Lewis dot structure. We also know carbon only makes 4 bonds. But we also see, you know, there are no available p orbitals either to do any sort of pi bonds. And so now this is looking at double bonds. So this could be for ethylene here. This would be one example. So now looking at ethylene, so what's our hybridization of carbon? So sp2, and it's really important to realize that it's sp2 since these structures are going to be planar. And so because it's sp2, we can see that. And so again, we said it was just our s plus now 2 of our p orbitals. To give us that planar sp2 lobes. And so that's shown here. So notice, right, this is planar. So this is just showing a carbon double bond, but if we were looking at ethylene, right, our hydrogen would be here. So that would be bonded to our sp2, creating a sigma bond. So just like here, hydrogen, so sigma bond, sigma bond, sigma bond. And of course we see we have this orbital overlap for one of our bonds here. And then how do we get a double bond though? What orbital do we have available to bond? PZ. So we could call it PZ. I prefer PZ goes in this way just because highest order, but you could call it PZ, you could call it PY, PX, P whatever, but just know, right, we have one p orbital that did not go into mixing, and now that p orbital is prime for our pi bond interaction. So that's where we get, again, that second bond now. So questions on this? Does it feel like review after chapter 8? And so now practice on formate for a second. So draw out what formate looks like with your Lewis dot structure, and then draw those orbitals. What's the hybridization on carbon? What's the hybridization of oxygen? how our drawing's going. So we should have something that hopefully looks like this, at least for the Lewis dot structure. And so now looking at our Lewis dot structure, so what's the hybridization on oxygen? So sp2. What's our hybridization on our carbon? So sp2. And so now that's telling us that the whole overall formate molecule is going to be planar. Since we have nothing, tetrahedral sticking out, so everything's just in the plane. And so then we could draw, right, our sp2 hybridized orbitals. So that's my carbon, oxygen. So we have our lone pairs, and two of them. Again, direct interaction, so that's our sigma bond there. And then, of course, these are bonded with our hydrogens, so sigma bond, sigma bond. And so what orbital then is available? How do we make that double bond? So once again, we have another P going. So of course, I try to draw this in just a flat down view. So right, our sp2 is sitting in the plane of the paper. And now we have to imagine, we'll call it, py, going up and down out of the plane of the board. And so we have py available on both of those. And so again, now that gives us our pi bond. And so now we see, oh, that's where our double bond came from that pi bond. And so again, we can say this is overall a planar molecule. We can visualize the geometry, or if you were, making your little, what's it called, molecules, you would see that too, that it's planar. I'm not sure why I threw this on there. Probably just a reminder of our trans versus cis isomers. So trans just being opposite. But again, these are both just sp2. The only difference is their arrangement. So obviously they're not imposable. So we have different isomers. And so we've already done CN before, but let's look at acetonitrile and see if you can draw that one out. So HCN, and that's not acetonitrile. Sorry. There we go. Sorry. H3CCN. There we go. So let's see, so how are your structures looking? So I'll just start with the Lewis dot structure. See. So did we get something that looks like this? So just making sure each carbon has 4 bonds is kind of the key point here. And so now what's our hybridization on this first carbon here? Someone's having way too much fun. So what's our hybridization on this carbon? So sp3, so we know that this is going to have a tetrahedral geometry, so not planar, right? Some sort of 3D. And then what's our hybridization on this carbon? So sp, what about this nitrogen?
SP2.
Oh,
Oh, SP.
unless you meant sp as well. And so now we can draw again what that looks like, what orbitals are interacting. So I'll just start with this kind of tetrahedral one. And so we know, again, those are just bonding with the hydrogen, not very exciting. Sigma bonds. Now we have our next carbon, so that's going to be sp hybridized, so something like that. So we have a making, right, 1 sigma bond there. Now we have our nitrogen. So nitrogen, also sp2 hybridized, so lone pairs. And then it's making our sigma bond here. And so how do we get a triple bond? What's left over? So px and py. And so now we can see, yes, we have 2 available orbitals. So we'll call this py to make 1 pi bond. And again, you could swap the labeling if you like this px. So 1 pi bond, and then drawing it, trying to come in and out. Again, are available, we'll call this px. Again, you can swap them, whatever makes you happy. And so now we can see, yes, we did make a triple bond. We had the appropriate orbitals to do so.
Can you do an MO diagram for one of the ones that we just did, just to like combine the 2 ideas, like this drawing with the MO diagram?
So like this whole thing, or?
Or like maybe the one before this one that was not quite as complex.
Yeah,
Just
so.
like connect the 2 ideas.
So that's kind of like the tricky thing about, and like the limitation of MO theories, you can only put 2 pieces at a time together. And so like we could look at, like CN, for example, and do just that MO diagram. Do you want to do that?
Sure.
So let's do that. And then we'll look at, so let's just compare.
I mean, unless I'm the only one that is confused about the MO diagrams, in which case,
Oh, I doubt you're the only one confused. So yeah, try CN now and see what that little fragment looks like. And then we'll put some other pictures. Actually, we should probably do CN with a minus charge. That'll make more sense for pairing it with the methyl. And that'll give you a better number of electrons.
Would this have mixing?
Yeah, you would assume mixing because you have a carbon and a nitrogen, so those are both sp mixing. It gets a little trickier if you have, like, for example, when we looked at CO, it may not be entirely obvious that we have SP mixing. And again, that's why there's like computational chemistry to give you a better idea. And that's the other thing. So we didn't really talk about it when we were doing WebMO, but if you remember, like, do you remember the bases set that you had to pick? Well, anyways, basically the more complicated your basis set is, it means like the more mixing it tends to involve, or like the more accurate it's supposed to be, but then it also takes longer. So there's always a balance. So I'll kind of start sketching it out so you can compare how yours is looking. And again, since nitrogen's slightly more electronegative, I'm going to try to put these p orbitals a little bit lower. I always feel this is like ASMR time, you know, gently drawing. Maybe I just get too zen drawing like Emma's. All right, so we should have something that looks roughly like that. 1, 2, 3, 4, 5, 6, 7, 8. So again, always double check that you can count. And then we have a negative charge, so I should have added in another electron somewhere. I'll just throw that onto here. So we have, right, 4 plus 5 plus our negative charge. So we have 10 total electrons, right, in the system. And so we'll just start at the bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so now this is kind of interesting. And I don't know if this will answer some of your questions. Hopefully it will. And so part of this is if we were to run like a WebMO calculation too, this would give us a better picture. And so again, right now we're looking at this, and perhaps I should have drawn this a little better. And so I want to emphasize, so right, we don't have a lot of electron density in the center. Oh, I misdrew that, sorry. One more time. So right, even though they're in phase, but we've minimized electron density in the center. And so all that means, right, is your electron density is located on the outside. And so this is why I say, right, it's formally bonding, but it's almost essentially kind of a non-bonding orbital since the electrons are going to be on the end. But then to kind of get a more refined picture, you would want to run like WebMO or something. And so I pulled up a diagram to show you what I mean by that. And so now this is the orbitals. And so carbon is on the left like we have it. Nitrogen is on the right. And so if you notice, right, this occupied orbital is mainly centered on the carbon. So now this is telling us that the carbon, that's where it's going to bond. So that's why when we attach it to like the methyl for acetonitrile, it attaches at the carbon, or at least that's another reason. So now, right, it's saying like, hey, we have our HOMO here, and now we can bond with something. Yes?
So, on Tuesday, some of the things we did, we definitely for a bond order a half. What would like the half bond?
So a half would just, it depends on, right, your bond order. And so all that means, like, because if you're comparing like a half bond versus a single bond, so half is going to be weaker because it's like barely held together, so we would expect it to be longer. A bond order of 1 should be shorter, like 1.5, shorter than that, then 2, then 2.5, 3. So it just gets smaller and smaller. So that's all that bond order is formally saying. And that's like the other thing. It's like, you know, these bond orders, that's just a way for us to quantify it. And really, it's all just like electron density and probability. And then we're just kind of comparing bond lengths. But yeah, so that shows you why it attaches at the carbon then. So then, right, when we're looking at this structure, we know, okay, the electron density is here, and that's where it can, again, attach now with our, like, methyl group.
I'm getting a bond order of 4.
So what?
Because only one, and only electrons occupying one anti-bond.
So 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2. Yeah, so make sure you label these. So this is, again, formally anti-bonding, even though, so we go back to this little diagram. So it's kind of showing us, so this is our bonding orbital down at the bottom, and then this is our anti-bonding. And so both of these are more centered on the atoms themselves. And so again, trying to minimize that electron density in the center. So we should have a bond order of 3 for this one. So let's look at more pretty pictures. So now let's look at benzene. And so this is kind of more math for a second, but then we'll answer again, like, why the heck do we care? And we'll just kind of try to take a simplified view with pretty pictures. And so all this is the different ways that we can draw our p orbitals now mathematically. And so if we draw benzene again, and let's just refresh ourselves. Well, what is benzene? So we said benzene was that ring. So most commonly, when chemists are feeling laziest, it's drawn like this. All that's saying is a delocalized pi system. And we could also draw it for, again, more clarity of those double bonds. And again, resonance arrows just showing that you can move those double bonds round and round and round until you're satisfied or gone loopy. And so now what this is showing is, so this is now the fully symmetric. And again, this is just all math. It's like, what are all the combinations? And so this one at the bottom is going to be the lowest in energy, just because they're all in the same shading, so they're all in the same phase. And so now this would be down at the bottom, known as 0 nodes. Then up at the top, you can draw 2. So these are degenerate orbitals on this next line, so B and C. So you could either draw a plane across here, and so that's this one over here, C. So these would be in phase, but now these ones across the node are out of phase, but in phase with each other, like that. So that's what that's showing here, with the positive and negative signs. Or mathematically, you can also draw a node down the center. So again, both of these have 1 nodes. And so if I draw it down the center, that one doesn't matter because the orientation doesn't matter. But then these two would be opposite. So these are the same if they're on the same side of the node. Now they're opposite. And continue on. So now this has 2 nodes. And so we could do nodes like that. So that's drawn here. So these are out of phase with each other. These don't matter. Out of phase. Oops. I feel like I drew something funny. Oh, this one I drew wrong. Sorry. It's like, that doesn't make sense. Okay, like that. And then our other combination. So now our other way to draw 2 nodes. Sorry, I have to draw a better hexagon for myself. So we could also have 2 nodes going down the center here. So 1, 2. So now this is out of phase. These 2 are in phase. Oops, would help. Sorry, my cord's also not helping me. So these are in phase. This is out of phase again. And then out of phase. Out of phase. So they just, notice they just switch right at every node. So this was the top shaded, now it's the bottom shaded, top shaded again, bottom shaded. And again, 2 nodes. So that's mathematically the same. And then this one now has all 3 nodes. And so that means none of them are the same. They all just alternate. So up, down, up, down, up, down. So now those are all out of phase with each other. So this totally breaks that pi symmetry. And so now the next question is, well, why the heck do I even care? And so let's look at why. And so now, again, this would be kind of beyond the scope of where this is going and what you want to be able to do. So there's a compound that exists. And so it's called chromium, or bisbenzene chromium. And it's drawn, or it's written like this. And so this A to 6 here, this just means that it's bonded to all 6. So, and so you have some sort of chromium, and you kind of draw it where it's like in the center, showing that it's bonded to all of those. So it's like head on. It looks like a sandwich. So these are actually called sandwich compounds. But again, the powerful thing is then you can tell what's bonding. And so how you would kind of do this, at least without math, without invoking anything else, is you're just kind of looking at what d orbitals would be appropriate. And so let's just start with dz squared. So dz squared looks something like that. So a shaded donut center and unshaded outside. And then we find that that would match up. So we're trying to think, right, sandwich compound. So that means this fully symmetric one can go on top. So this is primed to match. And so it would just be bonding with this orbital right here. So of course, if we have a sandwich, the same thing's going on bottom. But what you can imagine, and I'm just going to redraw it for a second, is again, you're just matching up shading, is, well, we have this fully symmetric possibility, and it's all unshaded at the bottom. It's all unshaded at the top here, so that can bond. So basically, right, this is sandwiching down on top of your z orbital, and so that z orbital is bonding with all of those. And they're all, again, the same color, so they all match up. They're in phase, so they can bond like that. And then, let's see, so we have other orbitals available. So chromium also has px and py. And so px and py, right, they could bond like with this one. So if it's going, so now we have one node. So right, if px is going this way, it could bond with all those on top. And so notice, right, how the shading's different. Let me kind of redraw this, but so if I take this, oh, come on. So if we take this, so again, you're just kind of looking at the top ones here, but chromium also has like p orbitals that are available. So if you wanted to call this, right, px, so it's going like that. And remember, the p orbitals have opposite shading, and that matches with what we have here. So the top part is shaded, so that matches with this px orbital, and then the px, right, the unshaded part now matches with the other half of that, so that can bond. So same thing with this other half over here. So then we could do, so this is basically the same thing, it's just in the other direction. So where it's unshaded and shaded, and so that would match up with py. So again, same sort of thing. And again, we're just looking at this pictorially, but that's where it's going. It's just like you're just matching the shading, seeing which ones can interact. And so if we look at another one, so I'm going to redraw one of our other pictures for a second. So we had this one where we had 2 nodes. Man, who is revving their engine out there? And so we have, right, some funky shading like that, but we could get some interaction with our dxy orbital. So xy lies in the plane like this. And so with the shading, so dxy, oops. And again, you can see if that dxy is coming in, so it's on top like this, and so it could match up. So this is the same shading as this is the same shading, this is the same shading, this is the same shading. And so I really should have plopped this on top. Let's see if I can plot that. So again, you can imagine this orbital just kind of plopping on top there to give you the appropriate bonding. So does that at least kind of make sense? And so in this class, we're not going to bother. So you would have to go a little bit deeper to get like a proper MO diagram. And so that's where the symmetry elements would come into play, but that's all inorganic chemistry. But all I want you to appreciate right now is we can just kind of take these picture representations and just like literally match them up based on the shading. And again, it's super powerful because it explains so much without having to run a calculation. And so if you wanted to go into it more in depth, I'm more than happy to go through it. But a lot of it that you would need to properly do it is kind of like beyond the scope. But again, I just want you to appreciate there are pretty pictures, and then those pretty pictures can match up with the orbitals that we know. We can draw these, and then we can explain, how these compounds came together, why they're bonding, who's bonding with what. And so again, it's just super powerful for back of the envelope calculations. All right, let's go ahead and take our 10-minute break, and then we'll come back, do our quiz. Hopefully it's simple enough. It's just like geometry stuff. So you can have, your notes. I would definitely have your Vesper cheat sheet out so you can remind yourself of the geometry. So yeah, take your 10 minutes, and then I will go ahead and stop this stream here.